Everybody, welcome to our latest. Just to remind you, we are going to begin, and I've got my friend and colleague Yoram Cohen here, but a little housekeeping to begin with. We record these webinars, so this will be available to you and anybody else that you want to send a link to on the NAWI YouTube channel. And we just request that you stay muted during the presentation. And if you have questions, which I know you will, put those questions into the chat as we are going along. And then at the end, I will invite you to come off mute, and then you can ask your question directly to Yoram and me. And also, if you found us through some link that somebody sent you, I know we have a bunch of outside guests listening to today's webinar. Do follow us on LinkedIn at National Alliance for Water Innovation, that link right there. That way, for future webinars, you can always get an alert when we have a future webinar. And speaking of which, as I said, follow us on LinkedIn. You can zap this QR code and find the link to join the NAWI Alliance LinkedIn page. And also, if you're curious about some of our older webinars, you can go to our YouTube channel found here. We have content dating all the way back to the start of the program, but this webinar series has now been going on for 5 years. Can you believe it? So a lot of really interesting developments in water and water treatment. As we always have to do, I have to explain that this views and opinion in front of the next person. So there we go. That's the disclaimer. And to tell you, next month, on July 15th, we have our next monthly webinar series on water tap. And it's with Dr. Adam Attia and the water tap team. Those of you who don't know, who aren't part of the NAWI program, water tap has been a major software platform that the NAWI community has built to do very quantitative, very rigorous techno-economic analysis of advanced water treatment systems. And so Adam is going to share with us not just what the latest is with the software platform, but we conducted a learning academy this winter. And that learning academy, we have a whole bunch of people who went through and are now doing projects. So we'll talk a little bit about some of the practical projects that people are performing with the water tap tool. So don't miss that. Next month, Wednesday, July 15th, 11 a.m. Pacific. And I'm going to stop sharing and invite my colleague, Professor Yoram Cohen, to set up his slides, and we will begin. And I'll simply say that I got a special place in my heart for this project, Project 510. And the reason it happened is I was looking for NAWI cost share money from California's Department of Water Resources back in 2019. And Nancy Vogel stared me in the eye and said, "Peter, what are you going to do for small systems, especially in California? We need help." And then Professor Yoram Cohen and his team showed up with this amazing project, and this is what we're going to talk about today. So I have designated myself principal cheerleader to accompany Dr. Yoram Cohen and his team, principal investigator. Yoram, welcome to the webinar series. Next slide. And Yoram, tell us a little bit about your team.
So our team included UCLA, California State University at San Bernardino, and of course the Lawrence Berkeley National Laboratory. And there were many students and participants whose images are not on here. They work with us and they went forward with their careers and have all contributed to this work, which I will describe to you.
Excellent. And Yoram, just want to notice, I saw Bilal Khan is in the audience as well. So Bilal, feel free to speak up as we go forward. Next slide, please. All right, so we're talking about a major problem that is across the United States, nitrate contamination in shallow aquifers. Nitrate contamination is most often a result of fertilization for agricultural districts. Next slide. And it is becoming recognized as a major health hazard, specifically for rural communities across the United States. Next slide. In California, we have thousands of groundwater wells. Many of our smaller communities utilize groundwater as their sole source of water, and we can see several thousand of these wells in the SAFER database that are above the MCL. When we look at small water systems up to 50 connections or up to 20 connections, you can see the many, many hundreds that are at risk or failing right now. An interesting point when we look at the distribution, and we don't think this is unique to California, but a lot of these small systems that are really facing great difficulty with nitrate contamination, they tend to be clustered. And so we'll come back to that. It's a very important theme. Next tab, Yoram. And then, of course, there is salt. Now, when Yoram made this figure, I was kind of startled to see that, normally when we think about desalination and reverse osmosis, we think about taking seawater, 35 grams of salt, and converting it to fresh water. But in California, in inland California and coastal California, we have vast amounts of brackish groundwater where the salinity is too high for us to use for drinking water or for some agricultural purposes. And then look here, even the Colorado River water is 700 to 1,000 milligrams per liter. So salt is part of our water system. And into this challenging situation comes none other than Dr. Yoram Cohen. Next. Here pictured before his appearance at the 1981 Zoot Suit riot at UCLA. Professor Cohen has been a landmark figure in desalination across the world, and we were so delighted when he and his team approached NAWI in 2021 with a proposal to build on a project that had previously been funded by the State Water Resources Control Board under Proposition 50. Yoram, welcome to the program, and tell us, I'm going to tell a little bit more. Thank you. No, keep going. One of the reasons why we were so eager to get this project funded was our 20th century water systems are really marvels of engineering, design, and construction. We have large-scale centralized treatment and centralized distribution, and that works great, especially for urban communities, and that's where the bulk of people live. However, next slide. When we get into agricultural basins, we tend to see smaller communities, and they have a dual challenge of having smaller populations and lower economic base. So they have a difficulty in operating sometimes more advanced water treatment. And as we said before, a lot of these basins are challenged with nitrate contamination, as well as a host of other naturally occurring contaminants or other agricultural products. Next slide. The issue is particularly acute for small and very small agricultural communities. In this case, clusters of small workers clustered together. These communities are the lifeblood and the backbone of our agricultural production in California. And yet they're least well served by the current centralized water treatment systems. Their communities typically are clustered around an individual water well, often a shallow water well, and these are the sorts of wells that are most vulnerable to nitrate contamination as well as other contaminants. And as I said, into this challenging situation came Yoram Cohen and his team. Next slide. Yoram, let's talk about small systems for a second. So walk us through this slide.
Yeah. So basically, Peter, I mean, we are very well versed and used to centralized systems that serve large population, industrial centers, and also somewhat smaller satellite systems that are also, in many respects, are centralized for their small population center. But on the other extreme, we have small communities that are not part of a centralized system, either water treatment or sewage treatment. And therefore, those communities kind of fall in between the cracks, and that creates a real problem. They don't have the person power, the technical ability to really take care of their own small system, or they may not even have a water treatment system in their locality. So there are challenges, and the challenges for those small distributed systems would be obviously the cost. They need to meet drinking water standards, for potable water, and it's important to avoid interruptions in the delivery of water. And those systems have to be able to operate 24/7, whether they operate continuously or intermittently. And therefore, there's also the issue of management of the treatment residual. If we treat this water using standard technology such as RO or NF or even ion exchange, we have to deal with residual streams. So that creates a challenge. And of course, as a result, there are also regulatory requirements and constraints that will impact the operation and the cost. So those are the challenges that we are faced with, and the important need to really help those small communities that cannot help themselves.
Take it away from here.
So we have worked in California, primarily in the northern part of California over the years, and developed and deployed various systems for agricultural drainage water treatment and desalination, for cooling water in electricity generation plants, also for seawater. Worked with the U.S. Navy to do that, as well as small system that you see at the top here for expeditionary units, as well as for greenhouse irrigation. And out of that, we realized that operation was really the key, and the ability to have autonomous systems that are self-adaptive is critical for distributed water systems where you don't have an operator on site 24/7. So from that, the system that I'm going to talk to you about today, or the systems, really were born out of that experience and a lot of headaches over the years. So we approached a number of communities, and I'll tell you about this story in a minute, but I thought that it'll be useful to show you right here. Those communities that we have selected for this project are between Soledad and Salinas. Fairly small communities, as you can see here, from 16 to 36 residents, and their water is contaminated with nitrate in two of the communities, up to about 6 to 8 times the allowable limit, and the salinity is above that of drinking water, secondary MCL. Their water consumption is between 200-300 gallons per day up to about 6,000 gallons per day. So those are the things that we have to work with. One of the things to realize immediately is that water usage is temporally variable, as you can see in the plot here for 3 of the sites. So when you design a system and its operation, you have to take that into account. So with that in mind, the thought about what it is that one would do and treat water in these communities is as follows. You have water from the well for the existing water system in those communities. It goes into a pressure tank, and from the pressure tank, of course, to the residential units, and the sanitary water from the houses or the residential units will then be discharged into a septic tank. Now, in the septic tank, what happens is the septic tank is under anoxic conditions, and therefore nitrate that enters a septic tank is denitrified to nitrogen that is then released, and the ammonium nitrate, of course, that is released to the leach field can then lead to formation of nitrate. So now the question is, if I have nitrate in the well and we are removing this nitrate, what happens to nitrate in the septic tank? Now, although there is science to indicate what I just told you, this was an important element to prove, and I will cover that as we move forward. So the treatment approach is you put in a treatment system, in this case, an RO system, between the residential units and the well. Water is treated, and the product water is then used by the community, and the concentrate will end up in the septic tank, as will the sanitary water. So basically, we're taking the raw water, splitting it into 2 streams, and then combining them together. And the argument here, which is important from a regulatory viewpoint, was to prove that we are not making things worse in the septic system, because the nitrate will be denitrified. So in fact, we are cleaning the water. Okay.
Well, also, Yorm, the fact is that all the nitrate was ending up in the wastewater in the first
Absolutely.
phase. And now we're simply taking the nitrate and other contaminants and bypassing the people in the house. So, it's a simple but very important concept. We can take those pollutants and keep them away from people.
Exactly. And so, Peter, what we forgot to tell the audience that this presentation will have the form of basically a podcast.
That's right. You and I are going to be
Right.
talking through
Where
this whole
Peter and
thing,
I will
right?
be talking to each
Yeah.
other. So, so we already covered that point, and now, uh, when you work on this project and you put it together, of course, you have research questions. And the research question, the important one is, can small scale type system, those systems provide safe and affordable water? And how will they be managed, maintained, operated? Is the technology good enough? What is the actual capital cost and the operating costs? Therefore, is it a viable or affordable solution that will be appropriate for small communities in California? So based on this question, the project goals were then to start with a single system, to expand it to 3 systems, and that's where really the involvement with NAWI came into play, as to how do we expand it to 3 systems and then manage them as a network, get the actual cost that is involved, and refine strategies for increasing systems reliability, remote monitoring, and develop soft sensors that are really critical here. And we'll cover that in a few minutes. And of course, ask the question, or try to answer the question, is it feasible to expand the automation and the infrastructure for those systems to let it grow to a much larger network of systems, or as we call a virtual water district? And what I should say is, when we started with this project, we did not have AI, we did not have the level of cloud services that we have today. And so things have obviously evolved over time. What's important in the project is to work with project stakeholders, of course, the property owners, the residents, state and county, the various water boards, even the building departments in the county, and various representatives, to work with non-profit organization, including arranging for replacement water for the communities while the project was still building, and to work with other groups in order to communicate with the residents and to build trust. And of course, it wouldn't be possible without the support of NAWI, the Department of Water Resources, and of course, all the students, the postdoc, the contractors that work with us over the years. And of course, last but not least, the Lawrence Berkeley National Laboratory, that has made a major contribution in assessing not just the life cycle, the life cycle or life cycle analysis, and the potential impact of such system on emission of greenhouse gases, and how can we reduce energy costs or electricity costs. So with that, I mentioned that community outreach is critical. I won't belabor that point, but I would say that we've been at it from the very, very early stages of the project, of selecting the communities. So we toured the entire region and talked to many different communities to identify those that are willing to work with us, but also to be able to answer the questions and build trust. And when I say be able to answer the questions and build trust, this is very important. It goes beyond the technical aspects, to the point where community members trusted us to such an extent that they thought that we know everything, and where members would come to me and say, we have a question, please come. And I thought they have a question about water. I would go to their home, and they would say, well, what do you think about this electrical system that I'm trying to upgrade here? What should I do? Right?
Yeah.
Well, so of course we had to walk a very, very
But they've been great partners. And again, for all practical purposes, Yorm, we are providing the water supply for these communities, and it's a very important thing for them in their lives.
Absolutely.
Yeah.
So, although not part of the work that we did with NAWI, but early on, we actually put one of those mobile system that I showed you on a van and drove to the community.
Right. Should I leave this on for you? You be biz? Okay.
Sorry, Emma Payne. We might suggest that you mute yourself. Thank you.
We drove by and actually did treatment on site and had water drinking parties with the community because we
That's
had to
nice.
convince them that that's water is safe. So of course I was the first one to drink it.
Okay.
So so the major element of the project is to install, operate, and of course measure, on all aspects. And this was a key, and we will talk about that. So the main component is, of course, to do the technological work, develop the system, deploy them, have all the sensors, controls, and the central, private cloud for monitoring those systems. Get all the information that we need in order to be able to determine the capital and operational expenditures so that we can arrive at the levelized cost of water. So with that in mind, just to remind you that the first system that we installed was in 2020, the second and third in 2022. So systems have been operated, from about 3.5, now it's almost 4 years, 4 to 5 years, which is a significant period. So I know that everybody is gung-ho on learning about water treatment, but I wanted you to know that before you can do the water treatment, you have to make sure that you have the site infrastructure that is properly done. So those of you that have built your own homes, you would know what is involved. Since I've had experience in building multiple homes over the years, I thought no problem, it'll be easy to do, without realizing that the regulatory aspects in that part of California was going to be a big headache. But we were able to do that. So you can see, work that is done on site, the piping, the trenching, and of course, all the storage tanks. And one important thing is that we installed septic tank sampling basin in order, to prove that there is denitrification that is ongoing in the septic tanks. And that had very important implications that you will hear about shortly. So I already said there was site investigation, community engagement, getting all the appropriate permits, and of course, designing the system layout, all the electrical, the plumbing, and working with the contractors to do that. And, ultimately, once that is done, then you can install the treatment.
And Yoram, let me just emphasize here, this is one of the important aspects of this project is UCLA did or oversaw all these works. So UCLA had all the receipts, which meant we could do a very accurate capital cost. So our analysis doesn't just include the cost of the parts, it includes all the aspects of siting, installation, et cetera.
Precisely, and that is important, especially if one approaches a new community, to be able to inform, the community as to what would be involved, and what the cost, would be. Yeah. So now we're getting into the actual treatment system. So I will show you a simplified view of it. So basically, what happens in the system is that we take water from the well into a feed tank, then into the treatment system, the RO. However, what we have is a recycle of the concentrate in that system. And of course, the concentrate portion of will be discharged to a septic tank. And what I'm not showing you here is that only water that meets the regulatory limit is diverted into the product water tank that you see in here. So once it's in the product water tank, another part of the system, which is also we have to take care of in terms of all the controls for that system, is delivering water to the community when is needed. They use pressure tank. Those are bladder tanks in order to build the pressure to deliver the water to the distribution system. And so once there is a need, once the pressure is at a given level or below a given level, then the delivery pump, would push water into those tanks.
And you're let me make an added point that, beyond the RO system, you are also having to take care of and satisfy all the regular requirements for drinking water
absolutely
in California. So adequate chlorination and hold a residual disinfectant. You all tested to make sure that you weren't liberating copper or any lead from the system. So you followed essentially all the regulatory requirements of a public drinking water system.
In addition to bacterial tests in order to sure that the water is safe. In addition to even testing water at the tap in the residential units, in order to ensure the regulators that there's no leaching of lead and copper, because we came in right after the big problem that arose in Michigan, right?
Yeah.
So
let's keep going. I know we're at.
So now let's move forward and say that the system is completely instrumented. There are roughly about 33 sensors in that system, and when we look at the operation of the system, those are the different sensors for conductivity, temperature, flow rate, pressure. This becomes very important when you look at the distribution. It's normalized here because, as I'll show you later, we use one system to learn about the operation and then apply it to another system.
Yeah, so let me just point out here, this diagram shows you, audience members, the range of each of these parameters. So it shows you that these small systems actually experience much wider ranges in a lot of these operational parameters as the water's going through the treatment train. And that's critical to understand as we develop the platform technology.
Okay, so very quickly, this is just a screenshot of the web dashboard for one of the systems, so we can actually look at the system in real time. And then if we click on any one of those sensors, we can see the current and the history of, in this case, the nitrate level, or if we look at the permeate flow rate, then we can get the history here. Now you can see that there are breaks in here because the system operation is intermittent. But what I want you to see here is that when I talk about a treatment system, it's actually three components. There is, the entire feed system, cleaning the system through flushing with permeate, but there is also the distribution system and the post-treatment of the produced water in here. So Peter mentioned chlorination, but there's also remineralization in order to stabilize the pH and put calcium back into the system. So with that, we can not only operate the system where we can access them individually, but we can also look at the system collectively via a web dashboard. So the main technical elements in here, which I will cover, the Fluoro system, which is the actual RO-based system, the monitoring, which I've already described to you, nitrate passage analysis and self-sensor development. I will mention that briefly. And of course, transfer learning, which was really important for rapid deployment and shortening the commissioning periods. So the Fluoro system, flexible RO. Basically, the idea was a number of years back, before we started with this project, is how can we reduce the size of a system and still allow us to have a very, very high level of flexibility in terms of covering a wide range of recovery. So in this particular system, what happens is that the concentrate, of course, is then recycled back to the feed. And when we want to reduce energy consumption and also reduce the ratings for the feed pump, one can insert a pressure intensifier, which basically transfer energy or pressure energy back into the feed and depressurizes the concentrate, which then feeds into the feed side of the pump. And that gives tremendous flexibility in terms of system operation. So in fact, as a result of that, and I'll try and go through this quickly, by saying that the system overall recovery is just a single pass recovery times 1 plus the recycle ratio. So in this particular case, we can operate whereby the normalized feed to the elements is essentially the same. It's a normalized value of 1. Then we have the concentrate, and then we can vary the recycle flow in the system by readjusting or by adjusting the recycle flow. We can therefore be able to also see that the row feed can be adjusted, and of course the permeate productivity can be maintained. And so here I'm showing you going all the way to 100. Of course, this is not feasible because of various issues, as everybody knows, with regard to buildup of osmotic pressure, but also mineral scaling. Point is that with that system, you can operate over a very wide range of salinities. Here I'm showing it for just one system, going all the way from seawater to very low brackish water. But the key is that we can, for whatever the inlet pressure to the elements is required, utilize a pump of much lower pressure. So in this case, you're seeing 30 plus bar pressure that is needed for the RO, elements, and that can be achieved with a pump that delivers only about 6.5 pump pressure. And that's
let's talk about this a second, Yoram. So the key element and the key benefit of the Flaro architecture is you can use one standard platform and address a wide range of incoming water quality, and you can also adjust, like a throttle, the production rate by the fraction that you recycle in the system. And as you said, with the small energy recovery device, you can use relatively low cost, low pressure pumps, and yet pressurize that the concentrate up and boost that. So it really means that you can use one standard package and apply it in a bunch of different environments. That's really key.
True, and it is also important, Peter, for when you realize that those communities may grow or decrease in size over time, that their water consumption may change as well, and water quality may change. So all of that becomes
yeah. And in fact, Yoram, you have some of these communities that are very seasonal. So you might have only a single handful of occupants during some of the year, and it might swell. Again, these are some of the practical challenges when you get to small systems with relatively small number of households. You can't average it over a large number of households. Anyway, please continue.
Anyhow, so for those of you that are that like complicated figures, there's one on the left. I'm not going to go through it, but basically this is a pictorial representation of the overall cyber infrastructure for the systems. But the main point that I wanted to make here is that in terms of operations, we've delivered about 7 million gallons of safe potable water to date, and those systems have provided with incredible amount of data. Roughly about 90 million data samples, each one consisting of 33 input sensors and process tags, which translate to about 3 billion, actually over 3 billion data points.
You hear that, data nerds? All the data nerds in the audience are flipping out, like, oh, all that operational data. That's right. It becomes critical, doesn't it? It becomes critical.
Absolutely. So we get data every 2 to 5 seconds, right, from the system.
Yeah.
Now, this is important when you're developing models to describe those systems and to provide self-sensors. So
okay, let me just stop you right there, and just because I know we have technical people and non-technical people.
Yeah.
In order for these systems to work, you also have to build a computer model that predicts how the system performs, because then you could always compare your actual numbers to what the computer is predicting. But in order to build that computer model, you need a large volume of data. And that's what we've developed here. But also, Yoram, explain about the 4 modes in which this system operates.
Yeah. So because I showed you at the beginning that the water use pattern is variable, right? And therefore the treatment system does not work continuously. Also, you have constrained storage. So if we have a storage of about, let's say 5,000 gallons, once it's full, the system has to stop. And so there are modes where, you know, the system may be shut down, and for various reasons, we don't let the system work more than 10 hours. You know, when it works for 10 hours, we shut it down, we flush it, and then we'll start again. Now, so there is a shutdown, there's a permeate flush, and then there's a startup when the system has to start, and then you get to production. Now, the other than production, all those periods are short, but they're very important, and they're very important because you don't want to basically deliver water that doesn't meet the regulatory standards during any one of those periods. Okay?
In other words, during startup or shutdown, you don't want to squirt a little untreated water through the system. At all the times, the system has to maintain that high water quality.
Right. And when you're developing a model, you want to make sure that the model not only is accurate, but you don't want to pollute the model with variables that are not needed. Okay.
Yeah.
And so here, I won't go through the details here. Here you see some of the variables, their pressures at different points, flow rates, conductivity in here for the startup. And then you see it for the, you know, for the second mode, which is permeate production. So you see that there are a few more variables in here. Then you see it, that the different modes share some of the same variables, but they're slightly different, okay? And for those of you that are interested, I'll be happy to talk to you a bit more about it, about the mechanistic reasons for all of these. Now, so when you look at the system, what you basically see is that there is a system startup, which is fairly short. Then there is a production period. Now,
Okay, hold on. System startup, I see up here 1.5 minutes. Okay, so about 90 seconds to start.
right.
Okay.
And then it'll operate for about 8 hours or so, right? And
Okay.
then there is a shutdown period.
Okay, about 1 minute to shut down.
And then
Right?
the flushing period. Now, those periods can change slightly because we monitor during startup the quality of the water. And so we're only going to go into production as long as, you know, once the water quality is met. So there can be slight variations. But one of the things that you see in here is that during shutdown, there is a spike, right? At the beginning, there's a spike in the salt concentration and a spike in the nitrate level. In fact, over many cycles, as I'm showing you on the right, it's difficult to see, but we're looking at predicted versus observed. What I want you to see is that there are spikes in the nitrate level that, you know, approach, and in some cases they actually overshoot the regulatory limit. So the regulators have asked us, you know, to actually set 8 milligrams per liter of nitrate as the operational limit, even though the actual regulatory limit is 10. Why? For safety. Okay. And so that becomes important.
So what happens during those periods of spike where the product water is above the that 8 milligrams per liter?
So that's a good question. So during that period, the water is basically diverted into the septic system.
So basically, it's just for it's a minute or less. It's a very small portion of time that the water
It could
gets
be a minute.
shunted over there.
In our experience, it can sometimes go up to 3 minutes. It depends on. So that is important. Also, why is it that we need to model? Is we want to know what is the longest period that to expect, you know, for the startup and for the shutdown, so that in the event that a sensor fails, right, we will use a conservative, okay, approach. Now, at the bottom, you see basically what are predictions of the observed versus.
Yeah, so for all of you people who are not nerds in the audience, when you see that diagonal line, that shows you that the prediction and the actual reality are highly correlated, and that R squared, for those of you who don't remember your statistics, that shows you the degree to which the two are matching. So R squared numbers of 0.9 or 0.92 means there is a high match between what the model is predicting and the system is actually doing.
Yeah, and so that is important because it means that we can check with the models that we have, we can check on system performance compared to the actual physical sensors, and that will allow us to also ascertain whether or not there is a problem. Now, of course, when we do that, we have to realize that we have multiple systems.
Yeah, so you build a model, you've calibrated the model at one site. The next innovation is about how do we take that model and adapt it to the next site down the road.
Absolutely. This is critical. Now, you may ask, why would you even want to do that, right? Well, our initial commissioning period was about 6 months, okay, or 6 months, maybe a little bit longer.
With all this testing and sampling and more testing and more sampling, yeah.
And that is very tedious, but also very costly. So we thought, is there a way to accelerate this process? If we can show that we can forecast, system behavior, and that in fact our forecast, meets reality.
And the other thing, Yoram, this is why this is so important. If you built a new system from scratch with a different design, you'd have to go through that all over again, right? But when you use the same standard platform, you could take the knowledge set built on one site and move right down the road to the next site and get up and running.
Absolutely. So here, basically, this is one site. So site A actually is in Salinas, and then we develop a model, and then what we would like to do is transfer this model to a site in near Soledad. The difference between the systems, slightly different in capacity. One had 2 spiral wound elements, the other had 3 spiral wound elements. So we go through this transfer learning, and basically what it means is that we take about a week or 2 weeks of data from the new site, and we use that to slightly tune the model that already exists from the first site. And so what I'm going to show you here is that when we do that, so now I'm looking at site B, I'm adding another site, the third site that you will see it. So we start, essentially with the initial model forecasting, and you see the R² of about 0.94. This is also for nitrate, but you see that we have a decline in the model accuracy. If we don't retrain, then model accuracy begins to deteriorate over time. So we're going here, you see, for quite a long period, about 365 days, right? A full year. So what do? We set a threshold that say we will not allow, to utilize the model below a certain level of performance, and then we retrained. And when that level of performance declines, we retrain again. And so roughly, we're talking about, not just from this example, but overall that we would have to retrain every 50 to 100 days, which basically you can think about it as a recalibration of the soft sensors.
Yeah, so in other words, physical sensors have to be recalibrated with standard solutions. Soft sensors, so these data models, need to be periodically recalibrated as they drift away from the initial conditions. So yeah, makes perfect sense.
And if you ask why do you need to retrain if it's the same system, remember what I showed you at the beginning about the data distribution, is because if we transfer the model based on data that is, say, at the beginning of the fall, right? Then by the time that we get to the winter, conditions change, temperature changes, the rate at which people are using water changes, water quality may change. So that's why you have to keep that going. So
yeah, let's keep going. I know we've got we're at 15 minutes before.
Okay, so with that in mind, I'm going to, basically jump.
A lot of work. Let's just say a lot of technical work went into building what we call a soft sensor, a way of accurately predicting nitrate passage.
And so you can see in here the key element is that when you have soft sensors, it allows you to do multiple things. One is you can correlate, for example, in this case, nitrate versus salinity. So if one sensor fails to work, you can use the other in order to fill in the missing data, or to infer if the predictions show you that the actual measurements are way off, then you can use that for fall detection. But there is another important element to this: cost. A nitrate sensor is very expensive. Okay, it's in the order of 10,000 to 15,000, depending on what.
Oh,
type.
and guess what? They don't work that well, by the way.
Well, you have to
Sorry,
recalibrate.
sorry, Hawk. Yeah.
Yeah, you have to recalibrate. So and then you have a connectivity sensor, which is much cheaper. So
And connectivity sensors are dead nuts. They're much simpler device, much
Absolutely.
longer performing. So yeah, you're basically using a robust, reliable, simple sensor to infer the performance of something that's hard to measure.
So for those of you that are wondering, if you know, a nitrate sensor could be 15 to 20% of the actual water treatment costs, excluding the site infrastructure. That's huge, right? And so those are considerations that one has to bring in. So
So this is the last innovation, right? This is the concentrate management.
So here, over a prolonged period of time, we determined that denitrification was, on the average, 90%, plus. And so we are denitrifying the nitrate that goes in and basically confirm this. And as a result of that, this study really convinced, the regulators that you can use the septic system for accommodating a discharge from the RO system. And as a result of that, a general waiver, was issued in by the Central Coast Water Board, and basically approved, or I should say, supported by the State Water Resources Control Board. That basically means that you can deploy an RO system and discharge into a septic tank for up to a capacity of 10,000 gallons per day without the need for a special permit.
And I mean, you told me this when it first happened, and I didn't quite appreciate it, but everybody, you need to understand just how profound this is. Reverse osmosis or these other membrane technologies will produce a brine waste stream that is basically impossible to get rid of. Now there's a safe place to discharge it into the septic itself. And that's a huge unlock, but particularly for small scale systems. Somebody asked earlier, is that per septic tank? I think it is, Yoram.
Yes,
so if you
yes,
had a larger community with 2 septic systems and 2 leach fields, you could do 10,000 in each.
Yes. So that becomes very, very, very important. So I'm going to go through this very quickly just to give you a visual, of the system. And you can see that all the communities are in the midst of agricultural fields. You can see that this is not just building a small system, but you basically build a whole treatment complex, right? And this is another site. Again, the community is in the midst of the agricultural area, and this is, the third one. So again, a community that is in the midst of the agricultural areas. So with that, I wanted to just to let you know that aside from all the monitoring, it was very important to actually do a lot of manual sampling at the very beginning by a state certified laboratory. I won't dwell on this, but you see all the points where sampling had to be taken, including from the septic, sampling basins. And that's what you need if you want to basically have systems approved for delivering drinking water. And that becomes a key. So the water that was produced met all the regulatory standards. And the key, to tell you in here is that the water, was produced, you can see in here, and here, and here, and here, with respect to nitrate and salinity, way below the regulatory limit.
And look at that. So those X's, those green X's are the water quality for nitrate for the city of Salinas and the salinity in the city of Salinas. So the water we're producing, these 3 small communities, is actually better than the municipal water available in the nearby town. Better water quality.
And that is very important. those of you that are ready to invest, here is CapEx.
Invest your time, friends. Yeah. So here's literally the money story. The total system CapEx, all installed from basically clearing off the lawn to the final system, is there.
And what you see in terms of the OPEX, that the labor cost is really the major part. The actual cost is between $2 to $3 per cubic meter. Now,
How does that compare, Yoram?
I'm glad you asked.
Oh,
So,
before we
but-
do,
but-
let's talk
but-
about
but-
let's
but
talk about
before-
the analysis, right?
Yeah, but before we do that, we wanted everybody to believe, those numbers. So those numbers are not taken from any estimates. They are taken from actual values. We design, develop, contracted, operated, and own those systems. So we have all the receipts, for the capital, for the operational, expenditures, and of course, all the way to site infrastructure and the cost of maintenance, and the remote monitoring. So with that, I want to say that aside from that, we don't have time to go over it, but LBL also, that was part of this project, has done incredible analysis to actually demonstrate or show that one can decrease the energy costs, the electricity costs, through optimized scheduling of operation, because there are differences in prices of electricity between night and day, for example. And also that, which was very interesting, is the greenhouse gas emissions. I actually lower for wellhead treatment relative to solution that has been used in some places, a partial solution for bottled water.
Yeah.
And that is important.
No trucks.
No trucks.
That's great.
And here, Peter.
Okay, so here's the comparison. Your systems, Yoram, here at the top, $2 to $3 per cubic meter. In the Salinas Valley, it's 2 to 4 for municipal water. And across California, it's 2 to 6. So this is at the low end of the cost scale.
That's correct. And if you think about consolidation, in some cases, the communities are too far away from the closest connection point to a central system. Cost is about $700, $700,000 per kilometer.
And people like, Steve Waite can tell you is on the phone that he thinks that number's off. It's about twice that now.
Yeah, that's a number, Peter, is a number that is cited by the California Water Board, but it doesn't include the cost of planning, administration, connection fees, line fees, and so on, and whatever water costs there's going to be associated with that delivered water.
Right.
And of course, bottled water, well, this is, you can look at the numbers. That's absurd, right?
Yeah.
In terms of cost, and you're not going to bathe in bottled water, right?
Well, we've got 5 minutes. Let's
right.
speed to the end here.
So we're done.
Yeah.
And I just want to tell you that, that the question is whether greater economics of scale could be achieved, with a cluster, with standardization, and via design improvement. I don't know why this is. Okay, via design.
Okay, go back. Yeah, back up. So basically, we think these costs could be better when you create more of these systems. First of all, your unit production cost for the hardware is going to go down. You're going to have a lot of learning curve and installation, and then you can amortize qualified operators amongst a larger number of these systems, and they can go around like a milk run. And how often, typically, is our one operator, Andy, touching these systems?
Visit the systems once a month, right?
Once a month.
Yeah.
Once a month.
Yeah.
Interesting.
So
that's great.
With that,
okay, let me kind of go my thing. So next frontier, Yoram, I want to just tab through these things. So one of the reasons why I wanted to be part of this presentation is that we are really excited by this result. We really think we have an economical solution, especially for these hard to serve small communities. And our next phase is to build a larger framework so we can truly validate the cost and performance of these systems. So we are currently building a plan to do a phase 3 program to deploy 20 to 30 of these systems. We'd love to do it in Monterey and Santa Cruz counties. We'll improve the AI and optimization monitoring. Keep going, Yoram. Standardize the system architecture. We can also, facilitate greater community support and capacity building. We can actually have local people learn to use these systems, reduce long-term costs. Keep going. And most importantly, kind of solidify a regulatory pathway for this approach to be adopted in other of the water board districts in California, as well as seeking a way to show other people. So we're currently seeking project partners. We will be looking for project sponsorship. Obviously, Prop 4 funding in California is one thing that we're going to be seeking. Okay, let's take us out. Yoram, why don't you just do the victory lap here?
Yeah, so rugged, reliable systems that we've talked about, that are simple to operate, remotely monitored. We rely on machine learning support for decision support, fault detection, soft sensors. We talked about that. Regulatory compliance, which is very critical. And of course, safe discharge of our residual stream into the septic system.
Yeah.
And what you see at the top here was a drinking party a few months ago, several months ago.
We like to drink on this project. Water, that is. Clean water. Yoram, thanks very much. I see we've had a number of questions, and I know we're at the top of our hours, and some of you might might need to dodge. So what I'm going to do, I'm going to answer a couple of the quick questions first, and then I'm going to invite you to unmute, and then you can ask your question directly. But one little question, Emily asked, are there any concerns about salt loading? Emily, the whole point of this approach is it's the same salt that's going into the septic system, because the water, the salt is coming from the well. It just previously was going through the house and getting exposed to the people. So there's no net difference in mass balance of the salt that's being put back in the septic system. So that's really one of the critical things.
Yes, Peter, we're not generating new salt.
That's right. That's right. A bunch of people, let's see. I'm going to invite Rashmina William, if you are still on. Rashmina, can you unmute yourself and you can ask some of your questions. Hello.
Hi, thanks, Peter. Appreciate it. So I had two questions for you both. The first is about scaling. So Yoram, it's lovely to meet you. One of the multiple hats I wear is as part of an organization that helps to scale technologies through piloting and trials. So I was wondering what your plan is to scale the project beyond these three systems. And then my other question for you was what sort of training and what organizations are you working with in terms of training for operators in some of these small systems, especially given the volume of data that you're creating here?
Great. So Rashmina, I'll take the first half of the question and then Yoram will take the second. So as I said, what our vision is with three systems, we've demonstrated a lot, but we really need to see what we call the creation of a virtual water district fully demonstrated. That is to say, geographically disparate individual systems, but all managed under a uniform system with common operators traveling to all the systems, common maintenance. And we are able to do that because we're using a base platform of hardware that's consistent across the installations. It doesn't have to be exact, but the base platform and the data infrastructure allows us to make this virtual water district. So that's the vision for what we call phase 3. Yoram, why don't you talk about the requirements for operators?
So for operators, I mean, obviously, for a system that has a lot of technology, you need to have an understanding of the system. But today, one of the things that we can do and prepare to do, and in fact, my colleague who is contributed to this and is listening today, Dr. Bilal Khan, has already started to look at the issue of developing basically an AI assistant that, based on what we have developed, that is our manuals, all the information that we have in terms of system operation design, all of our operating reports through the years to develop a system that would basically be able to assist, operators in understanding what to do when things happen and how to go through the process. But we also are investing, right now in developing an approach where we would actually train an operator. We are working with a very highly skilled operator right now. At the beginning, it was UCLA, our students, postdoc that were the operators. They're all certified as T2 operators by the state. So we gain a lot of experience. And then we transitioned to basically a professional technical operator that has been working on the system and has also worked with us on the construction of those systems. So I think that we can do it. When we started, AI did not exist, at least not in the way that it is today. So I think that the possibilities are endless.
I see you've got a hand up from Andre. Andre, where are you today? And don't forget to unmute yourself. There you are.
Yeah, so I also have a question about scaling.
Andre, where are you physically?
I'm in Colorado.
Colorado. Excellent. Welcome.
Yes.
I would have thought Texas, but now it's...
Yeah, so I have a question about mineral scaling. What scalants did you encounter, and what are your cleaning procedures? So I've seen that there is, it seems like a 7-hour soak, permeate soak that you do after 8 hours of operation. Do you also have, do you do any acid cleaning or caustic cleaning during any periodic cleaning?
Good question. Peter and I were debating whether to cover this or not. So we don't first we don't soak for 7 hours. We go through a permeate flush. Now in those particular communities, and I've worked in this area for a long time, but in this region, it's calcium carbonate that is the main. We do use anti-scalant, right, in those systems, and we do go through permeate flushing. Now, we do not, for those systems, and I don't want to spend too much time here, but this is based on our analysis. We do, one of our PhD students, Nora Markey, that is part of the team. I showed this picture at the beginning. Actually, develop an approach for optimal scheduling of membrane replacement. For those small systems, it's a lot cheaper to replace the membranes than to clean them, okay? Because the cost of cleaning is way above, okay, the cost of replacement. We can replace once every, 3 years. If we were to clean, it would be a disaster cost-wise. So we can afford to have a bit of degradation in performance. Of course, because of that, you'll be paying a little bit more in terms of electricity or energy costs. So you have to optimize that. Okay. But the cost that we showed in terms of the operational costs includes that.
Yeah.
Okay. So I would not recommend for small systems that are, of the order for those small communities of 5 elements to 8 elements. I would not recommend cleaning it. I've done.
Yeah. So yeah, that's another really interesting lesson, Andre. For large systems, CIP cycles and all those things, if you've got thousands of modules, makes sense.
Yeah.
When you've got small systems, you treat the module essentially as a consumable.
Yeah, because the cost involves, you bring chemicals right to the site, and then you have to clean, you have to flush, and then you have to get rid of those chemicals.
Yeah.
And so the cost of cleaning, it would take about a day or 2 days, depending on the system. Replacement, takes a few hours.
Yeah.
And so we are writing a paper on that, and if you get in touch with me, I'll make sure that we keep you on our mailing list.
Andre, does that answer your question? We're good?
Yeah, thank you.
Awesome. I see Mark Harrington asked a couple of questions. Mark, are you still on? You want to unmute yourself if you're still around? There you are.
Yeah.
You want to ask your questions?
Everyone, can you hear me all right?
Yes.
Yeah.
Yeah. First,
Where are you?
yeah,
First of all, Mark, where are you physically?
I'm physically out in Hawaii.
Excellent.
Yeah. So yeah, thanks for the presentation, Yoram. I actually took your class at UCLA about
Ooh, an
15 years
alum,
ago.
Yoram.
I hope I gave you a good grade.
Yeah, absolutely. So yeah, I think sparing some of the technical questions, I was curious about the vision for more large scale deployment of this. Would this be, you alluded to this virtual water district, following that analog, would these systems be like centrally owned and operated by a single entity? And like, how is that financed?
That's good. Great questions, Mark. And again, those questions of governance and like, is it organized like a municipal water district, et cetera, are really critical questions. And actually, one of the goals of our phase 3 program would be to resolve that. But Mark, from an operational cost, producing this water is comparable to the cost of muni water. So one element of this is small communities are willing to pay for clean, affordable drinking water, and we can produce clean, affordable drinking water with this technology. The question of who funds the capital cost, it depends a lot on whether how long these assets are going to be in place. So, for example, if you have $130,000 investment, and you know that this system is going to, that's the capital cost, and you're going to be running the system for an amortized lifespan of 10 years, and you amortize that cost over 10 years, you might actually be able to fold that capital cost into the cost of water. Of course, Mark, one of the other things that we focused on for this project is serving the communities that are least well served by centralized water treatment. And these are often the most economically vulnerable communities. And so in some cases, for example, some small communities of these small systems in California, they're actually on agricultural property, and it's actually worker housing. And so in those cases, the actual farm might be the one who buys and owns the equipment, and maybe even pays for it. In other cases, we're just dealing with rural property owners. In some cases, it might make sense to see if there can be philanthropic donations to pay for the capital cost, and then the operating cost can be paid by the residents. So that's kind of where we are so far. And I also want to just kind of introduce another not related, Ilana Cohen, who's joined the NAWI 510 team, who is going to be building out our program in the phase 3 program. So Ilana, you feel free to come on mute if you want to add more. But Mark, that's kind of where we are right now. Does that answer your question, or does it prompt more questions?
Yeah, a little bit of both, but thank you. I guess if I got a chance, one more technical question was, looking at the system, it obviously has a lot of bells and whistles in terms of instrumentation and monitoring, which on one hand seem like to operate this at a full scale with non-local operators, you want a lot of visibility to how the system's performing. But is there an opportunity that you guys see for once these systems go into more mass production, that the sensor or control element can be relaxed a little bit?
Or simplified? Yeah, that's a great question.
Simplified. Yeah.
Yoram, what do you think? I mean,
Yeah.
you've got this thing bristling with sensors.
Yeah,
Is that going to be necessary all the time?
No, definitely. I think that we can reduce the level of sensors, and that depends in part on the water source. Because if we're in a situation where water source quality changes significantly, on a temporal basis, then it's a different story compared to a place where the water quality basically is time invariant. Okay, so we have to take that into consideration, and that is really more of a regulatory issue, right? The stricter that their regulatory requirements, the more that you need to rely on your sensor to assure that everything is working as it should. But I gave one example. Remove a nitrate sensor, that's a huge cost, right?
Well, we don't have any nitrate sensors. The point is, Yoram, you're using salinity, you're using conductivity in lieu of nitrate.
No. I mean, yes. I mean, that's to do that. But we actually, as part of having those systems accepted, in this project, we actually installed real-time nitrate sensors in there. All right, in order to prove that we have a correlation between nitrate and conductivity. All right, so we
I see.
had to prove that. So so that by itself is a huge expense that can be reduced. Now, in terms of other components like actuators, I would not cut down on those, because the minute that you put in manual valves, then you need to have on-site operator. So there is room, to reduce costs, and I think that this is one thing that we are looking into. But remember, the cost of the system, is about, nearly well, not exactly 1/3, but getting close to that of the overall, cost, which includes the infrastructure. Okay, so we're talking about, for those small communities, about $55,000. If we remove a nitrate sensor, the systems are much cheaper. So there is room for engineering ingenuity, definitely.
Yeah, and that's what we hope to gain on the phase 3 part of the program is further cost reductions and design efficiencies, et cetera. So thank you all for that. I know we are past time. I'm going to ask if anybody else wants to ask their question. I know we've got a bunch of great questions here that we didn't get to everybody. Bruce Webster, are you over in San Rafael today, Bruce Webster? Is Bruce
speaking
still
to
on?
you from San Anselmo.
San Anselmo.
That's the
You want to ask
picture
your
of
question?
Dillon Beach behind me is a site that could potentially be a node.
Cool. That would be great. Well, yeah.
My one question was the instead of well water, this water is appropriative water rights and riparian water rights to take rain from the natural watershed collected in 50,000 gallon tanks, and that would be the source water instead of well water. I assume that's okay.
Yeah. Yeah.
Any source water.
Yeah. I mean, whether it's surface water or collected rainwater, the same, systems would work.
Yeah.
If it was surface water, I'd probably add a bit on the pre-treatment, maybe have a screen in there. But in terms of the overall operation, it would be pretty much the same.
Yeah, great.
Yeah.
If
So we got Tom
if you
Pancratz
make
on
it
the
to
line.
Marin, keep me
Oh,
in
sorry.
mind.
Go
I'll
ahead.
be
Keep
glad
going,
to-
Bruce. Sorry.
Yeah, I'll be glad to collaborate if you can,
Cool.
if Marin County can count.
Awesome. Well, you know where to find me, Bruce.
Yeah, I sure do.
Awesome. Let's see. I saw Tom Pancratz. I don't know if Tom, you want to unmute? Any thoughts there, Tom?
Well, I saw a couple. Can you hear me?
Yeah.
Okay. I saw someone ask a question about the pressure exchangers, and you called it a pressure intensifier. And I think for a system like this, it might be a good idea to just explain what that is.
Yeah.
Yoram.
Tell Yoram what that is. Somebody else asked, is this a small energy recovery device, a turbine? What is it?
No, it's not a turbine. It's a pressure exchanger. So essentially, it has a piston inside. Okay, that travel the length of the intensifier. Where you use the high pressure from the concentrate. To push the.
You had a name for it, though. You were telling me last week. What's the name of the?
I mean, you can in our case you can use a Clark pump.
Clark pump, right?
Yeah. So if you Google that, you can I mean, in fact, you can buy a Clark pump and build a system like that. What we have done is we combine that with a recycle stream, and that in order to give greater flexibility.
And that's one thing that's important here. Not only cost, this is a more cost-effective solution for this, but it's also flexible, and it'll serve somewhat the same purpose. I just thought bring that to people's attention. In case you're not.
That's really you're correct. That's really the key.
It is the key.
The energy reduction in energy costs is not so much of the issue or energy consumption, but it's more the flexibility of allowing you to operate over a wide range of salinity and to use a pump that is of lower pressure rating. So then you keep the CapEx, lower. That's really the key for those small communities.
Yeah.
Mhm.
Thanks. Thanks for showing up, Tom. By the way, if for those of you missed it, the Water Maven had an article about this project 2 weeks ago, so you can Google that. And I know we're coming to the end of our rope here in terms of time, but I want to thank everybody for attending. If anybody has a burning question, they absolutely will not be happy unless they get to ask their question. Raise your hands. If not, then we're going to sign off. Anybody?
I see a question from Carl Longley. Carl,
Carl.
yeah, nice to see you here, sort of.
Why do you say sort of? Carl's.
I mean, I don't see him in person,
That's true. Sort of, right.
So I see
There he is. Look, ask and you
that's
shall
it.
receive.
Yeah. So I see your question in there, and let me say that RO is, the nice thing about using RO, which EPA, the US EPA, in fact, indicates as a solution that is is recommended in this case, but RO can protect against multiple contaminants. I think you
Yeah.
mentioned arsenic. In fact, in one of the sites, we had all of a sudden an appearance of 1,2,3 TCP. It was at a low concentration, but the permeate was essentially
Right.
free,
The-
free of 1,2,3 TCP.
The
So
problem is when you concentrate this, you have a as waste.
Except, Carl,
And
the
this
water
is,
is the same water coming out of the well. We just split it and the people get to avoid the contaminant.
I don't think that'll fly with the regulatory folks here.
well, but
Well, that point, Carl, is a great point because Central Coast is one of the 9 water boards. So the question, I think another challenge question out to the audience today is which is the next water board territory that wants to take a look at this? Because we have underserved communities everywhere.
The other part is, I presume this is not in your library yet.
Which, the recording?
Yes.
No, we're not that good, Carl. Give us a week or two.
Okay, so once it's there, I'm going to send the address to some of the folks on the water board. I want them to look at it and get their opinion.
Carl, I'll come over and brief them. Seriously. I think that the Central Coast has been a great partner so far, but we recognize that every one of the boards needs to look at this from their own unique vantage point.
Well, they're confined to what they refer to as an in-valley solution.
Yeah.
Which means it comes in, very little of it goes out.
Yeah.
And so the question is, how do you address that? And that's a prime question.
Yeah. I think that this is worth discussing. There is always the option for having a treatment train. We're not trying to say that the membrane base is the only one, or that it should just be used on its own. For example,
and Yoram, also, your system might well have applicability on the east side of the basin, but the west side, which is a completely different geological soils picture, I think will require a different solution.